Hi students, let's start our discussion of electrostatics. In this particular video, we are going to discuss the most important topic of the entire electrostatics, behavior of conductors in electrostatics. How the conductors behave here in electrostatic equilibrium condition. So here it is very important to understand the things from the very base conceptual level. So point by point, we'll discuss them. Now, first of all, you see what happens when a conductor is placed in an external electric field that I am trying to explain you. Let us say you have any conductor, this one, any conductor, and solid conductor you can take, hollow conductor you can take, any, or I'll do one thing, I'll take it as this type of conductor. Now here in this conductor we have only here the conducting material. This blue color region is the conducting material, right? This blue color region. When this particular object will be placed in external electric field, like say this is the external electric field. Now what happens here when this external electric field has been placed, switched on? There will be some free electrons present here. I am representing those free electrons by these yellow circles, these circles. Everywhere free electrons will be there. Now these free electrons will start experiencing a force in this direction opposite to the electric field. They start experiencing the force in this direction. As a result, only where conducting material is present, only in this region, in this blue region. So as these electrons are moving opposite to the field direction, there will be some redistribution, rearrangement of charges takes place within the conductor. Here some negative charge appears. Say here some negative charge will appear because many electrons will accumulate here, right? And here some deficiency of electrons will take place. So if I say here the deficiency of electrons, that's why little positive charges, and here the excess of electrons, that's why negative charges, it will come. So redistribution of charge takes place. It is taking place up to where we are going to attain the electrostatic equilibrium. So electrostatic equilibrium means charges are not going to move. When the charges will not move, when the force on them will be zero. Now it is the dynamic equilibrium. Don't compare it. If the force zero, they can move with constant velocity. You will understand slowly this. So here to attain the electrostatic equilibrium condition, force on them must be zero. Force on them must be zero when the electric field intensity will become zero here in the bulk of the conductor, in this part. So in short, I can say, now you see here, when this conductor is placed in this external electric field, these electrons will move opposite to the electric field. Redistribution of charges will take place. As a result, negative charge comes here, positive charge appears here, and electrostatic equilibrium condition has been attained. So when a conductor is placed in an external electric field, redistribution of charges will take place to attain the electrostatic equilibrium condition, and this particular entire duration will take a fraction of millisecond. It is very fast. We don't bother for this time interval in which it is attaining the electrostatic equilibrium condition. So in short, I can say we people will consider that electrostatic equilibrium condition has been attained. In how much time? We don't bother about that small duration, right? Next point you see, and this also I have already told you, in to attain the electrostatic equilibrium condition, and in electrostatic equilibrium condition the electric field intensity inside the bulk of the conducting medium will become 0. So here this statement you can see, in electrostatic the electric field intensity inside the bulk of the conducting medium is 0. In electrostatic equilibrium condition, the electric field at all these points where the conducting medium is present is going to be 0. The charge on the conductor will distribute itself. In the example I have taken the neutral conductor, even if it will have some charge, that charge will distribution on the conductor in such a way that electric field intensity inside the conductor will become 0 wherever the conducting medium is present. So first point about this topic, whenever a conductor is placed in an external electric field or in electrostatic equilibrium condition, the charges on the conductor will distribute itself in such a way that in the bulk of the conducting medium electric field has to be 0, right? Say for example, one more example I'll take. Let us say this is a conductor, say solid conductor. No other charge is there anywhere. We have given some charge Q to it. This charge can be here, can be here, can be here, it can be anywhere. But it will distribute itself in such a way that at all inside points electric field has to be 0. For that to happen, charge has to be stored here only. And it will be stored as uniform because sigma is proportional to 1 upon r. We have already seen in one particular thing. So it will be stored here in a uniform way, right? But say for example, one point charge Q1 has come near to this conductor. Now, due to this, if it is uniformly distributed, here the field is 0. But due to this, it is non-zero. So the total field here becomes non-zero. So what will happen? The distribution of this charge on the surface, this charge on this surface will change itself. In which way? So that here the field inside will become 0. It is the total field inside the conductor has to be 0. In electrostatics, any charge given to the conductor will distribute in such a way that electric field inside the conductor in the bulk of the conducting medium will become 0. Right? Now, in electrostatics, the electric field is along the normal to conductors. If we are having the conductor surface, say like this, then at all the points, electric field will be along the normal in this way. Electric field is along the normal to the conductor surface. If it is positive charge, it is away from the surface. If it is negative charge, it is towards the surface. Electric potential is along the normal to the conductor surface. Now here we have seen electric field inside is 0 and here it is along the normal. It means if I write dV equal to minus E dot dr, if I use this, here the field is 0 inside the conductor. So by using this, I can say V is equal to constant, because dV equal to 0. So V equal to constant. It means potential at any point inside the conductor here, at all the points here, conductor is same and its value is same as that at the points on the surface. So we can also say conductor is an equipotential surface in electrostatics. In electrostatics, conductor is an equipotential surface. So 3 points, again summarizing. In electrostatic equilibrium condition, the charges will distribute on the conductor in such a way that electric field intensity in the bulk of the conductor is always 0. Bulk of the conductor means where the conducting material is present. This point I would like to explain again. Now see here, only here conducting material, where white shaded lines are there, here only conducting medium. At all these points electric field 0. Inside, this is we call the inside of the conductor. In many books people write like this way, that electric field in electrostatics, electric field inside the conductor is 0. So some students get doubt, this is inside. This is inside. So here it will be 0. In some cases here it will be 0. In some cases will be there where it can be non-zero also. We'll discuss that part also. But here in the bulk of the conducting medium, it will be 0 always. Actually there we want to say in electrostatics, electric field in the bulk of the conducting medium is 0, not inside the conductor. Inside the conductor, it can be 0 or it can be non-zero. So first point, in electrostatics, the redistribution of charge will take place in such a way that electric field intensity in the bulk of the conducting medium is 0. Electric field at the surface of the conductor is along the normal, and in electrostatics, conductor is an equipotential surface. Now, next point you see. Any excess charge given to a conductor resides only on its outer surface. If you have any solid or hollow conductor, whatever, and you are giving some charge to it, Q you are giving to it, then this charge will reside only on the outer surface. It cannot be inside. It cannot be in the bulk. It will be only residing on the outer surface only. Next property we have, whatever charge we are giving to a conductor, here it is meant only for isolated conductor. Isolated conductor. Remember, this particular statement is valid only for isolated conductor. So if we are having an isolated conductor, say like this, and isolated means nothing is present near to it, and we give some charge to it, then this is going to reside on its outer face. Here it is going to reside on its outer face. Now, depending upon the radius of curvature of this point, depending upon the radius of curvature at different points, let us say if I draw another shape like this. Now, this is spherical. This one is spherical. So radius of curvature is same at all the points. So radius of curvature is same. So sigma is here at any of the point is proportional to R. R is same everywhere. So sigma is same everywhere. Uniform charge distribution. But if you see that elliptical type object here, now here the radius of curvature are not same at all the points. Here if you see radius of curvature is very small, and here if you see the radius of curvature is very large. So radius of curvature is different at different points. So when the radius of curvature is different, then the charge distribution will be non-uniform. And here you can say charge distribution on this type of elliptical cavity type thing, charge redistribution will be non-uniform. Charge density is proportional to the radius of curvature. Charge density is proportional to the inversely proportional to the radius of curvature, and this is valid only for isolated conductor, not for non-isolated conductor. Now next point you take, electric field in the vicinity neighborhood of the conductor surface is sigma upon epsilon naught. Let us say any conductor surface, conductor like this, any conductor, and we are taking some charge has been given to it, which has been divided at different points with any surface charge density depending upon sigma is proportional to 1 upon r. If we consider one small element here, small part of the surface of the conductor, then electric field here will be sigma upon epsilon naught. Electric field at this particular point near to the conductor will be sigma upon epsilon naught, where sigma is the surface charge density at this location, where sigma is the surface charge density at the location where you are writing the electric field, right? So we can say it is sigma upon epsilon naught, where sigma is the local charge density. This doesn't mean that at this point, electric field is only due to this charge. Here the electric field is due to all these charges as well as this charge. This total electric field is sigma upon epsilon naught. It is not only due to this charge, it is due to entire charge on the sheet, on the other part of the object, and on this part of the object, right? Next we have the electric pressure. This is also a conceptual point. You consider any conductor surface like this, any conductor, and we have some, this point you take small surface element delta S, and here the charge density is sigma at this location. At this location it can be say sigma 1, at this location it can be say sigma 2. Then each and every part are repelling each other, which gives them rise the electric pressure. This electric pressure is sigma square upon 2 epsilon naught. Here it will be sigma 1 square upon 2 epsilon naught. Here it will be sigma 2 square upon 2 epsilon naught. This is the electric pressure. This is nothing but electric force. Electric force experienced by unit area. And this electric force is from where? Let us say we are finding the electric pressure at this particular area. Then who exerts the electric force here? This remaining part of the conductor will exert the electric force here. So electric force, I can say, the exerted by remaining part of the conductor. So sigma square upon 2 epsilon naught is the electric pressure. Now, up till now we people were talking about a conductor without having any charge inside it, even though we have never mentioned it. But now coming the most important and very concluding statement about how to deal with the conductor's behavior. Now this statement, you see, this statement is sufficient to understand all the things. Any conductor, any conducting shell, please be careful on the lead, any conducting shell, this is the shell I am taking, right? Divides the entire space in two parts, inside and outside. This is the outside part, this is the inside part. Any conducting shell divides the entire space in two regions, inside and outside. Now these two regions are independent of each other in terms of electric field. Due to outside region, there is no net electric field at any inside point. Due to inside charges, there is no electric field at any outside point. Whatever happens outside the shell, that happens there. Whatever happens inside, it happens there. तुम अपने घर खुश, हम अपने घर खुश. We are not interfering in each other's life. Inside people happy there only. They are not disturbing the outside people. Outside people happy there only. They are not disturbing the inside people. Inside charges, they are not affected by outside charges. Outside charges not affected by inside charges. This we are talking in terms of net field. Individual interference will be there, right? But total effect of all outside charges at any inside point 0, total effect of all inside charges at any outside point is 0. So once again I am summarizing. Any conducting shell divides the entire space in two regions, inside and outside. These two regions, inside region and outside region, are independent in terms of electric field intensity. Electric field intensity at any inside point due to all outside charges 0, and at any outside point due to all inside charges is 0. Now I will take few examples, few questions, and then I'll explain it. Now here you take, this is a conducting shell. This is the conducting shell. There are few charges marked Q1, Q2, charge on the inner face of the conductor Q3, on this face Q3, charge on this face Q4, outer face, another charge Q5, another charge Q6. We are interested in marking the field intensity at point A, at point B, at point C. Now you see, electric field intensity at point A due to Q1 non-zero, due to Q2 non-zero, due to Q3 non-zero, due to Q4 non-zero, due to Q5 non-zero, due to Q6 non-zero. But electric field intensity at point A due to Q4 plus due to Q5 plus due to Q6 is 0. Understood? Due to Q4 non-zero, due to Q5 non-zero, due to Q6 alone non-zero, but due to 3 together, electric field intensity at point A will become 0. Understood, I hope? At point B, due to all 6 charges individually non-zero, but due to Q1 plus Q2 plus Q3 0, due to Q4 plus Q5 plus Q6 0. Total field 0, because here conducting medium is present. Electric field in the bulk of the conducting medium is 0. At point C, due to Q1, Q2, Q3, resultant of due to Q1, Q2, Q3 0. Due to Q4, Q5, Q6 non-zero. Resultant field at C is only due to Q4, Q5, Q6. due to Q1, Q2, Q3, it will become 0. At any of the point, field is contributed by all the charges. At every point, field is contributed by all the charges. But net resultant contribution due to all outside charges at any inside point 0 and vice versa. And remember, in the bulk of the conducting medium, electric field will be always 0. Electric field intensity in the bulk of the conducting medium will be always 0. Now let's take some basic situations. Let us consider this one conductor, okay? And we are considering, say this is a solid conductor. Solid conductor. And we have given some charge Q to it. Then that charge Q will be distributed on the outer surface. It will be here. Now since curvature is different at different points, so this distribution will be non-uniform distribution. Now one point charge Q naught is placed here outside. And we have marked one point P inside the conductor. And it is mentioned that this distance is R. It is mentioned this distance is R. And we have to find the electric field intensity at point P due to charge on conductor. This is what we have to find. Now, point P is inside the conductor where the conducting medium is present. So, net electric field at point P is equal to 0. Why it is 0? Because the field in the bulk of the conducting medium must be 0. Now, electric field intensity at this point will be due to this charge and due to this charge. Due to the charge on the conductor surface and due to Q naught. So, I can write electric field at point P is due to charge on sphere plus due to Q naught. And this vector 2 sum is 0. And this is what we have to find. We have to find. But this directly we can't find because this charge distribution is non-uniform. We don't know the shape of the conductor. We don't know the distance of different points of the conductor surface from point P. So this is directly not possible to find. But this is we can find. Electric field intensity at point P due to Q naught we can find. This will be equal to K Q naught upon R square. Let us say this point Q is S, then it will be in which direction? SP direction. Now sum of these two is 0. This we don't have any method to find. But this we have the basic formula to find. So what we can say this is equal to negative of this. That is electric field intensity at this point due to this charge on the surface of the conductor is KQ naught upon R square in which direction? In this direction towards the point S.